Hello there, and welcome to the Sleepy Space Channel. Tonight, we'll be drifting slowly outward, away from the warm, crowded middle of our galaxy, on a long, quiet walk toward its faraway edge. We will leave the bright disk behind us, one soft layer at a time, and travel through regions most people never picture at all. A great round cloud of ancient stars. A vast thin atmosphere of breathing gas. A family of small companion galaxies keeping their patient orbits in the dark. And we will ask a single gentle question the whole way out. Where does the Milky Way end? The answer, when we find it, will be softer than you expect. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Let the day fade gently away behind you. Let's begin. Part 1. The Sun's place in the galaxy. The journey to the edge of the Milky Way begins at the Sunday. Not because the Sun is the center of anything, but because it is where we are, and a survey of the galaxy must start from a known position. So the first task is to establish that position clearly before the journey moves outward from it. The Sun is a star. It is one of somewhere between 100 billion and 400 billion stars that make up the Milky Way. It is not at the center of the galaxy, and it is not at the edge. It sits a little more than halfway out from the core, in an ordinary stretch of the galaxy's flattened disk. That position, a little past the midpoint, is the starting point of this documentary, and it is worth understanding the structure that surrounds it before the journey begins. The Milky Way is a spiral galaxy. More precisely, it is a barred spiral. Its main body is an enormous flattened disk of stars, gas, and dust, rotating slowly in space. At its center is a thicker concentration of older stars, the central bulge, and crossing through that bulge is a straight bar of stars. From the ends of the bar, the spiral arms wind outward, curving through the disk in long, trailing curves. This classification, barred spiral, is shared by a large fraction of the galaxies in the universe. The Milky Way is, in its overall form, a common and well-understood type of galaxy. The disk is wide. It measures roughly 100,000 light-years from one side to the other. A light-year is the distance light travels in a year, and light is the fastest thing there is, so the scale of that number is difficult to hold. Light, leaving one rim of the galactic disk, would take 100,000 years to reach the opposite rim. The disk is the defining feature of the Milky Way, the part that gives the galaxy its name and its shape. To place that figure in context, consider the nearest star to the Sunday. It lies a little over 4 light-years away. The light now arriving from it left that star more than 4 years ago. And that star is, in galactic terms, immediately next door. The disk of the Milky Way is roughly 25,000 times wider than the distance to the nearest star. The galaxy is not merely large. It is large on a scale that requires the light-year as a unit, because no smaller unit would produce numbers that could be written down conveniently. Every distance in this documentary will be measured in light-years, and every light-year is itself a distance that light requires a full year to cross. Against that width, the disk is thin. It measures only a few thousand light-years from top to bottom, and most of the galaxy's stars are concentrated in an even thinner layer than that. Set against its 100,000 light-year width, the bright disk of the Milky Way is, in proportion, thinner than a sheet of paper. This thinness is the reason the galaxy appears the way it does in our own night sky. The faint band of light that crosses the sky on a clear, dark night, the band that gives the Milky Way its name, is the disk of the galaxy seen edge on from within it. The Earth is inside the thin disk, and a view along the length of the disk passes through a great depth of stars whose combined light blurs into that single soft band. A view perpendicular to the disk, by contrast, passes quickly out of it and shows far fewer stars. The shape of the night sky is a direct consequence of living inside a thin disk. The disk also contains the interstellar medium, the gas and dust that fill the space between the stars. This material is not evenly distributed. It is concentrated into clouds, some of them cold and dense, others warm and diffuse, and it is from the cold, dense clouds that new stars form. The interstellar medium is thickest within the spiral arms and along the central plane of the disk, and it is the reservoir from which the galaxy has been producing stars for billions of years. The number of stars in the disk is not known precisely, and the reason is informative. Most stars in the galaxy are small. The majority are red dwarfs, stars far smaller and dimmer and cooler than the Sun, burning slowly and faintly. They are too dim to count individually across galactic distances. The bright, prominent stars that are easy to see and easy to count are the rare ones. The true population of the galaxy is dominated by small, faint, long-lived stars, and so the total can only be estimated within a wide range. The dominance of red dwarfs has a further consequence worth noting. These small stars burn their fuel extremely slowly. A red dwarf can continue shining steadily for far longer than the current age of the universe, by a wide margin. The most common type of star in the Milky Way is therefore also the most durable. The bright, massive, luminous stars, the ones that define the appearance of the spiral arms, are short-lived by comparison, lasting only millions of years rather than billions. The galaxy's population is, in the main, an enormous number of small, faint, stable stars, accumulated over the galaxy's history and still shining. This is a useful fact to carry forward, because the outer regions of the galaxy, which this journey is traveling toward, are dominated by exactly this kind of old, faint, long-lived star. The spiral arms require a clear explanation, because they are often misunderstood. In images of spiral galaxies, the arms appear to be solid structures, like the spokes of a wheel. They are not. The spiral arms are patterns. They are regions where stars and gas are crowded together somewhat more densely than in the surrounding disk. Individual stars drift into an arm, remain within it for a time, and drift out again over millions of years. The arm itself persists as a pattern, a density wave moving slowly through the disk, even as the specific stars composing it continually change. This is worth restating because it is the first principle the journey will rely on. A spiral arm is a region of higher density, not a defined object. It has no edge. It fades smoothly into the less crowded disk around it. The structures of the galaxy are defined by density, not by hard boundaries, and density always changes gradually. This principle will return at every stage of the journey, and it will eventually provide the answer to the central question of this documentary. Because the arms are where matter crowds together, they are where new stars most often form, and where the brightest young stars illuminate the surrounding gas. The arms are the regions of the galaxy with the most active star formation, and they are, in consequence, the brightest and youngest-looking parts of the disk. Now, the Sun's specific position. The Sun lies approximately 26,000 light-years from the galactic center. It is not in the crowded, brilliant inner regions, where stars are packed closely and the sky would never fully darken. It is not in the sparse outer reaches either. It sits a little past the halfway point in the calmer outer portion of the disk. The Sun's location has a name. It lies in a feature called the Orion Arm, also known as the Orion Spur. The Orion Spur is not one of the galaxy's major arms. It is a smaller structure, a minor spiral feature situated between two larger arms, the Sagittarius Arm, which lies closer to the galactic center, and the Perseus Arm, which lies farther out. The Sun occupies this minor feature between the two major arms. This position has consequences for the night sky. The Sun's location in a relatively low-density region means the surrounding star field, while substantial, is not as crowded as it would be inside a major arm. The Sun is not stationary. The entire system, the Sun and its planets, and the stars surrounding it, orbits the galactic center. It moves at roughly 230 kilometers per second. That is a high speed by any ordinary measure, yet the orbit is so large that a single complete circuit takes between 200 and 250 million years. This single orbital period is called a galactic year. The galactic year is a useful measure of scale. The last time the Sun occupied this exact point in its orbit, roughly 250 million years ago, the Earth was a profoundly different world. The continents were arranged differently. The dominant forms of life were different. A single galactic year encompasses an entire chapter of a planet's history. The Sun has completed only about 20 such orbits in its entire existence, and the galaxy itself has completed a comparable number of rotations in the regions near the Sunday. The galaxy is old, but it is not so old that it has turned an uncountable number of times. It is a structure whose rotation can be counted. The Sun's immediate surroundings are worth noting because they are unusually clear. The Sun is situated within a region called the local bubble, a cavity of low-density gas within the interstellar medium. It was carved out long ago by the outward pressure of stars that ended their lives in the vicinity. The space immediately around the Sun is therefore emptier than much of the galactic disk. This is a local condition, a feature of the Sun's particular neighborhood, and not a property of the galaxy as a whole. The galactic center itself, 26,000 light-years inward from the Sun, is worth describing briefly because it defines the inner boundary of the structure this journey will traverse. At the center of the Milky Way is a concentration of stars, far denser than anything near the Sun, and at the precise center is a supermassive black hole, an object containing roughly 4 million times the mass of the Sun, compressed into a region smaller than the orbits of the planets. The entire galaxy, including the Sun, orbits this central region. The black hole's gravity does not, however, reach out and govern the whole galaxy. At the Sun's distance, the gravitational environment is determined by the combined mass of all the stars, gas, and dark matter interior to the Sun's orbit, not by the central black hole alone. The center is the densest, brightest, most crowded region of the galaxy. The journey runs in the opposite direction, outward, toward the sparest and faintest regions, and eventually past them. It is also worth establishing the galaxy's age, because the timescales involved will recur throughout the journey. The Milky Way is roughly 13 billion years old. It began to form not long, in cosmic terms, after the universe itself began. The oldest stars in the galaxy, which the journey will encounter in the stellar halo, date from that early era. The disk, with its ordered rotation, assembled later. The galaxy is therefore not only large in space, but extended in time. Its different components formed in different eras, and a journey outward through its structure is also, in part, a journey through its history. The Sun itself is an ordinary star. Among the galaxy's hundreds of billions of stars, it is a middling one, neither among the brightest nor the dimmest, neither the largest nor the smallest. It is a stable, average star, burning at a steady rate, of a type that exists in large numbers throughout the disk. There is nothing exceptional about the Sun's properties, its position, or its motion. It is a representative star in a representative location. That establishes the starting position. The Sun is an average star in a minor spiral feature, a little past the halfway point of the disk, within a low-density bubble, orbiting the galactic center once every 1/4 billion years. From here, the disk extends outward in every direction, and beyond the disk lies the rest of the galaxy, regions that never appear in the familiar photographs, regions far larger than the bright disk itself. The direction of the journey should be stated clearly. The survey will move outward, away from the galactic center, toward the rim of the disk and beyond it. It is the shorter of the two directions available. The Sun is closer to the disk's outer edge than to its center. But it is the direction that leads through every component of the galaxy in sequence, from the densest to the most diffuse, and it is the direction that leads to the answer the documentary is seeking. The journey will pass through the bright disk first, then the stellar halo, then the gaseous halo, then the region of the satellite galaxies, and finally, the dark matter halo, in that order, from the most familiar component to the least. One further point should be established before the journey begins concerning how the galaxy is observed at all. The Earth is inside the Milky Way. This makes certain measurements difficult. An observer outside the galaxy could photograph its complete structure directly. An observer inside it must reconstruct that structure indirectly, by measuring the distances and motions of individual stars, by mapping the gas, by tracing the orbits of distant objects, and by combining many such measurements into a model of the whole. The complete picture of the Milky Way that this documentary will present is the result of that reconstruction. It is well established, but it has been assembled from within, which is part of why some of the galaxy's components, the ones farthest from the Earth and the faintest, were the last to be mapped and are still the least precisely measured. The central question of this documentary is straightforward. Where does the Milky Way end? Where is the edge of the galaxy? To answer it, the journey moves outward from the Sun, through each region in turn, all the way to the galaxy's true limit. There is one principle to carry forward from this first part. The galaxy is built from density, and density fades gradually. Whether that fading ever amounts to a true edge, a defined line, is the question the rest of the journey will examine, region by region, to the outermost limit of the Milky Way. Part 2. Outward, through the bright disk. The journey begins by moving outward from the Sun, through the bright disk of the galaxy. This is the part of the Milky Way that appears in every photograph and every illustration. It is the part most people picture when they think of the galaxy. And it is the most densely populated region the journey will cross. Through the disk, the sky remains full of stars. The first structure the journey leaves behind is the Orion spur itself, the minor spiral feature in which the Sun resides. Moving outward, the next major structure is the Perseus arm, one of the galaxy's principal spiral arms. The route runs from the minor spur, across a less crowded gap, into a major arm. A spiral arm does not announce itself with a boundary. As established in the first part of this journey, the arms are regions of greater density, not solid objects, and they have no edges. Moving into the Perseus arm, the disk simply becomes gradually more crowded. The stars draw closer together. The gas and dust grow denser. There is no line to cross. The density rises smoothly until the surroundings qualify as an arm. This is the same principle that will, by the end of the journey, apply to the galaxy as a whole. If the arms have no edges, the galaxy's larger structures will prove to have none either. Within a spiral arm, the galaxy is at its most active. The denser gas clouds in the arms are able to collapse under their own gravity, and that collapse produces new stars. The arms are the primary sites of star formation in the Milky Way. The most massive of these newly formed stars are extremely luminous, and their intense radiation causes the surrounding gas to glow. These glowing clouds are the emission nebulae that appear in long exposure photographs as regions of soft, red, and green light. They are concentrated along the arms. The arms are the youngest-looking parts of the galaxy. There is a continuous cycle at work in the arms, and it is worth describing in full. A cloud of cold gas drifts through the disk and enters an arm. The increased density of the arm compresses the cloud and triggers its collapse. Over a span of millions of years, the cloud fragments and forms a cluster of new stars. The brightest and most massive of those stars illuminate the leftover gas, producing a visible nebula. Those massive stars are short-lived. After only a few million years, they exhaust their fuel and end their lives, while the cluster of fainter stars gradually disperses into the general population of the disk. The arm then moves on to compress the next cloud. This cycle of compression, collapse, star formation, and dispersal has operated along the spiral arms continuously for billions of years. It is the mechanism by which the galaxy converts its gas into stars. The Perseus arm, the major arm the journey is crossing, lies farther from the galactic center than the Sun does. Moving into it means moving outward, and it is worth registering that the journey, in passing from the Orion spur into the Perseus arm, has already begun the outward survey in earnest. The arm is not a destination. It is one of the regions the route passes through on the way to the disk's edge and beyond. It is important to note what lies between the arms. The space between spiral arms is not empty. It contains enormous numbers of stars, generally older and less luminous than the stars within the arms, orbiting the galactic center in the ordinary way. The arms are not where the stars are located. The arms are where star formation is concentrated and where the brightest stars are found. The disk between the arms remains densely populated. It is simply quieter and dimmer and older on average. The Sun itself, located on a minor spur between two major arms, occupies precisely this kind of in-between region. The galaxy's most common environment is not the bright arm but the quieter disk between arms. The colors present in the disk are worth noting. The young massive stars in the arms are blue-white, the color of stars burning at high temperature. The nebulae they illuminate glow in red and faint green. The older, more numerous stars of the general disk shine in yellow, orange, and red, the colors of cooler, more stable stars. A view across the disk combines all of these: the blue-white of the arms, the soft glow of the nebulae, and the steady yellow and orange of the older population that fills the space between. The dust of the disk also deserves a closer description, because it is more than an obstacle to observation. The dust consists of fine, solid grains, far smaller than grains of sand, distributed through the interstellar medium. It is mixed with the cold gas clouds, and it plays a direct role in star formation. Dust grains help the cold clouds shed heat, which allows them to collapse, and dust grains are also the surfaces on which some of the molecules of the interstellar medium form. The dust is not merely something that dims the view. It is a working component of the disk. involved in the process by which gas becomes stars. And the same dust, gathered in dense clouds, is what appears in photographs of the galaxy as the dark lanes threading through the bright disk. Those dark lanes are not gaps in the galaxy. They are dense concentrations of dust, blocking the light of the stars behind them. The structure of the disk also includes features at smaller scales than the spiral arms. Within the arms and between them, the disk contains star clusters, groups of stars that formed together from a single cloud and remain loosely associated for a time before dispersing. It contains individual nebulae at various stages, some actively forming stars, some the expanding remnants of stars that have ended their lives. And it contains the cold molecular clouds, the densest concentrations of gas, which are the specific sites where star formation begins. The disk is not a uniform sheet of stars. It is a structured, active region with its own internal features at every scale, continuously processing gas into stars. The journey passes through all of this on its way outward, and it is worth registering, because the regions beyond the disk, the halos, are by comparison far simpler and far quieter. The disk is the galaxy's most complex and most active component. The journey now leaves that complexity behind and moves toward the simpler, sparser, older, outer structure. As the journey continues outward, the first significant change becomes measurable. The disk begins to thin. This thinning occurs in more than one sense, and each is worth describing precisely because it is the first real evidence relevant to the central question of the galaxy's edge. First, the disk is layered in thickness. The Milky Way's disk is not a single uniform slab. It consists of a thin disk, only a few hundred light-years deep, which contains the younger stars and most of the gas, and a thick disk, a few thousand light-years deep, which contains older stars on more inclined orbits. The thin disk is the site of the galaxy's ongoing star formation. The thick disk is an older population, settled into place long ago, and it represents an earlier era of the galaxy's history. Second, and more significant for this journey, the disk thins with distance from the center. The density of stars is not uniform across the disk. It is highest near the galactic center and decreases steadily with distance outward. Moving outward from the Sun, the journey follows a continuous decline in stellar density. There is no point at which the stars abruptly stop. There is only a steady decrease, the population growing sparser with every increment of distance. The brightness of the disk, plotted against distance from the center, is not a step, but a slope, a long and continuous decline. The gas and dust thin as well. Because gas is the raw material for star formation, the outer disk, with less gas available, forms fewer new stars. Consequently, the average age of the stars increases with distance from the center. Near the Sun, the disk contains a mix of younger and older stars. Farther out, the younger population is largely absent, and the stars are predominantly older, long-lived stars in stable middle age. The outer disk is the quieter, older portion of the galaxy's bright structure, dominated by exactly the kind of small, durable, long-lived star described in the first part of this journey. At a distance of roughly 50,000 light-years from the center, the disk has grown notably fainter and sparser. Here, the outer disk displays two structural features that are worth documenting in detail, because both bear directly on the nature of the galaxy's edge. The first is the warp. The galactic disk is not perfectly flat. Near the center, it is very nearly flat, but the outer disk is warped. One side of the outer disk curves gradually upward, away from the central plane, and the opposite side curves gradually downward, so that the outer rim of the galaxy has a shallow, shaped distortion. The warp is attributed to the gravitational influence of the galaxy's satellite galaxies, which the journey will reach in a later part, and to the inflow of gas from outside the galaxy. The Milky Way's outer disk is not a flat, level plane. It is a curved and distorted one, shaped by the influence of structures beyond it. The second feature is the flare. With increasing distance from the center, the disk does not only grow fainter, it also grows thicker. The thin, well-defined disk near the Sun gradually broadens and increases in vertical extent toward the rim. This broadening is called the flare. The outer disk is therefore both fainter and thicker than the inner disk, sparse, warped, and broadened. The crisp, well-defined geometry of the inner disk gives way toward the rim to a structure that is more diffuse and harder to characterize precisely. These two features are the first direct evidence bearing on the central question of this documentary. The outer disk does not behave like the edge of a solid object. It is warped rather than flat, flared rather than sharp-edged, and continuously fading rather than abruptly ending. The closer the survey examines the outer disk, the less it resembles a defined boundary, and the more it resembles a gradual transition. The dust also thins with distance, and this has a measurable effect on observation. Throughout the disk, clouds of fine dust absorb and redden the light of more distant stars, an effect called extinction. The inner galaxy contains a great deal of dust, and that dust obscures a great deal of what lies behind it. The outer disk, with its sparse dust, offers a clearer line of sight. The few stars that remain there are observed plainly, without the heavy obscuration that affects observations toward the inner galaxy. By the outer disk, the night sky has changed substantially in character. The dense field of stars, visible from the Sun's position, has thinned considerably. The stars are fewer and farther apart, and the dark intervals between them are wider. This is the expected and well-understood consequence of declining stellar density. It is not the edge of the galaxy. It is the edge of the bright disk only, the first and nearest of several boundaries the journey will examine. The rotation of the disk is worth a note here, because it explains a feature of the spiral arms. The disk does not rotate as a solid body. The inner regions complete an orbit faster than the outer regions, a pattern called differential rotation. If the spiral arms were fixed material structures, differential rotation would wind them up tightly within a few rotations of the galaxy, and they would cease to be recognizable as arms. The fact that the arms remain open, well-defined spiral structures after many rotations is one of the clearest pieces of evidence that they are not material structures at all, but density patterns, waves that move through the disk at their own pace, independent of the orbital motion of any particular star. The stars move through the arms. The arms themselves persist. It is also worth considering the journey in terms of time. The route from the Sun outward to the edge of the bright disk spans more than 30,000 light-years. A signal traveling at the speed of light, the fastest speed possible, would take more than 30,000 years to cross it. The galaxy is not a structure that can be crossed quickly by anything. Even light, which crosses the distance from the Sun to the Earth in about 8 minutes, requires tens of thousands of years to move through the regions this part of the documentary surveys. Every increment of this journey outward is, in real terms, a span that light itself treats as long. The outer disk also marks a transition in the character of the galaxy. The inner galaxy is bright, crowded, actively forming stars, and in many directions obscured by dust. The outer disk is faint, sparse, settled, and clear. The journey is moving steadily from the galaxy's active star-forming inner regions toward its quieter, older, outer structure. The warp and the flare at the disk's rim are the first clear signs that the well-defined geometry of the inner galaxy does not extend all the way out, and that the outer galaxy is a more diffuse and less sharply defined kind of place. The bright disk does not end at this point in any abrupt sense. Faint streams of stars continue outward past the distance where the disk is conventionally said to end. The journey now approaches that conventional boundary directly, and the next part of the survey examines it, the edge of the bright stellar disk, and the reasons that boundary cannot be marked with a simple line. Part 3. The edge of the bright disk. The journey has reached the outer limit of the bright stellar disk. This is the first of the galaxy's several edges, and examining it directly reveals the central finding of this documentary. The Milky Way does not have a single edge. It has several, nested one within another, and each is a region of fading rather than a defined boundary. This part of the survey establishes why that is the case. Consider first what the word edge normally means. An edge is a property of solid objects. A table has an edge. A sheet of paper has an edge. A coastline is, approximately, an edge, a line where land gives way to sea. When the question is asked, where does the galaxy end, the word edge implies that kind of boundary, a definite line, with the galaxy on one side and empty space on the other. The question, as ordinarily phrased, assumes a boundary of that kind exists. A galaxy does not have that kind of structure. A galaxy is a gravitationally bound system, an enormous collection of stars, gas, and dark matter, densest at the center and decreasing in density outward in every direction. It has no surface. It has no boundary layer. The density simply declines with distance until it becomes indistinguishable from the background of intergalactic space. The galaxy does not end at a line. It thins. This is a direct consequence of the principle established in the first part of this journey. The galaxy is built from density, and density fades. A spiral arm has no edge because it is a density pattern. The bright disk has no sharp edge for the same reason. And, as the journey will demonstrate region by region, the galaxy as a whole has no sharp edge, because every component of it is defined by density, and density always declines gradually. It is worth being precise about why a structure built by gravity cannot have a sharp edge. Gravity does not switch off at a particular distance. Its strength decreases smoothly with distance from a mass, and it never reaches exactly zero. A structure assembled by gravity is therefore always densest, where the gravitational gathering is strongest, near the center, and progressively less dense outward, with no distance at which it abruptly stops. The gradual fading of every galactic component is the direct expression of the smooth, continuous weakening of gravity. There is no wall anywhere in the galaxy, because the force that assembled the galaxy has no wall. Because the galaxy fades rather than ends, it is necessary to speak of several edges, not one. Astronomers identify multiple boundaries depending on which component of the galaxy is being measured. There is the edge of the bright disk. There is the edge of the stellar halo. There is the edge of the gas. And there is the edge of the dark matter. Each lies at a different distance from the galactic center. Each is a real, measurable feature. None of them is a sharp line. The journey will cross all four in turn. The first is the boundary the survey has now reached, the edge of the bright disk. The bright disk is the component of the galaxy that dominates its appearance. It is the part that, viewed from a great distance, would still form the recognizable shape of a spiral galaxy. This bright disk fades out at a distance of roughly 50 to 60,000 light-years from the galactic center. That is the conventional figure for the edge of the disk. But the figure is approximate, and the reason matters. Even at and beyond that distance, faint streams and threads of stars continue outward. The bright disk has an outer region where its stars become genuinely scarce, but that region is a gradual decline, not a stopping point. Any specific distance assigned to the disk's edge is an approximation, a convention. A different measurement, using different criteria for where the disk should be said to end, would place the boundary somewhat farther in or farther out. The edge of the bright disk is an agreed figure, not a physical wall. At this distance, the stellar density has dropped substantially below the density near the Sunday. The dense star field of the inner disk has no counterpart here. An observer at the outer edge of the disk would see a sparse scattering of stars across a largely dark sky, each star widely separated from the next. The disk at this distance is a faint remnant of the structure it forms near the galactic center. It has not ended. Its density has declined to a low value. The night sky from the outer edge of the disk would differ from the sky seen from Earth in a further instructive way. From the Sun's position, a quarter of the way out, the band of the Milky Way crosses the whole sky, because the disk extends in every direction around the Sunday. From the outer edge of the disk would no longer surround the observer evenly. Looking inward, toward the galactic center, the observer would see the bright, crowded mass of the galaxy concentrated in one part of the sky. Looking outward, away from the center, the observer would see comparatively empty space. The galaxy would appear lopsided, gathered to one side. This is simply the perspective from near the edge of a structure rather than from within its body, and it confirms the same fact the density measurements give. The outer disk is genuinely the galaxy's faint periphery, not a central region. It is worth pausing on what the disk's edge represents in the history of the galaxy. The bright disk, formed by the gradual settling of gas into a rotating, flattened structure and the formation of stars within it. The outer edge of the disk marks, roughly, the outer limit of where that settling and that star formation reached. The disk did not form all at once, and it did not form uniformly. It grew, generally from the inside outward, over billions of years. The faint, sparse, warped, flared outer disk is the most recently assembled and least settled part of that structure, the disk's still forming frontier. Its diffuse and irregular character is not a flaw. It is the expected appearance of the outer edge of a structure that is still, slowly, being built. There is a further point worth documenting about the outermost disk stars. Not all of them originated in the Milky Way. Some stars in the outer disk began their existence in smaller galaxies, separate galaxies that approached the Milky Way and were gradually pulled apart by its gravity. Their stars were drawn out and incorporated into the outer regions of the Milky Way. Those stars now orbit as part of the galaxy, having arrived from elsewhere. The outer disk includes stars assembled from other galaxies entirely. The journey will examine this process directly in the next part, where its evidence is most clearly visible in the structures of the stellar halo. This also corrects a possible misconception about the outer galaxy. The edge of a galaxy is not a hazardous location. It is not a precipice. A star in the outer disk orbits the galactic center in a stable manner, exactly as the Sun does. A planet in the outer disk would experience stable days and years, governed by the same physics that governs the Earth. The word edge carries an implication of risk, of a drop, of ground running out. There is no such feature anywhere in the galaxy. The outer disk is simply a low-density region of the same stable, gravitationally bound structure that contains the Sunday. It is quieter and emptier than the inner disk, but it is not less stable. It is worth pausing on the scale already covered. The journey has moved from the Sun, at 26,000 light-years from the center, out to the edge of the bright disk at 50 to 60,000 light-years. That is a distance of more than 30,000 light-years. Light itself would take more than 30,000 years to cross the ground the survey has covered in this part of the journey. And this is only the first edge. The galaxy extends much farther still. The 4 edges identified in this part of the survey deserve to be stated together, because the rest of the journey consists of crossing them in turn, and it is useful to have the full sequence in mind. The first is the edge of the bright disk, the boundary the survey has now reached. The second is the edge of the stellar halo, the limit of the galaxy measured by its stars. The third is the edge of the gaseous halo, the limit of the galaxy measured by its diffuse gas. The fourth is the edge of the dark matter halo, the outermost limit of all, measured by the galaxy's gravitational influence. These 4 are not competing answers to the question of where the galaxy ends. They are 4 real, separate boundaries, each belonging to a different component of the galaxy, each at a greater distance than the last. The galaxy genuinely has all 4. The question, properly answered, is not which one is the edge, but the recognition that the galaxy is a layered structure with several. There is a reason the bright disk is the edge most people would name, and it is worth addressing directly. The bright disk is the only component of the galaxy that is conspicuous. It contains the bright stars, the spiral arms, the glowing nebulae. It is what photographs record and what illustrations depict. The stellar halo is too faint to be conspicuous. The gaseous halo and the dark matter halo emit no visible light at all. So the edge of the bright disk has, by default, become the edge people picture. But that is a consequence of which component is easiest to see, not a statement about the structure of the galaxy. The bright disk is the most visible component. It is not the largest, and its edge is not the galaxy's true limit. The journey continues precisely in order to cross the boundaries that visibility alone would cause one to miss. It is worth comparing the Milky Way's edge to the edges of other galaxies, because the comparison reinforces the point. When astronomers photograph a distant spiral galaxy, the galaxy appears in the image to have a definite edge, a point where the bright spiral gives way to dark sky. But that apparent edge is a limitation of the photograph, not a property of the galaxy. It is simply the distance at which the galaxy's light becomes too faint for the instrument to record. A longer exposure, or a more sensitive instrument, reveals fainter outer regions, and the apparent edge moves outward. Every galaxy fades gradually. The sharp edges seen in images are artifacts of detection limits, not real boundaries. The Milky Way is no exception, and the difference is only that, observed from within, its gradual fading can be measured directly rather than inferred from a photograph. There is a further consequence worth drawing out. Because the edge of the bright disk is a convention rather than a physical feature, the figure of 50 to 60,000 light-years is best understood as a description of where the disk has become faint, not as a statement of where the galaxy stops. The disk's stars continue to exist beyond that distance, in steadily decreasing numbers. The convention marks the region where, for practical purposes of measurement and description, the bright disk is no longer the dominant feature. It is a useful figure, but it is not a wall, and treating it as a wall would misrepresent the structure of the galaxy. Recent and detailed mapping of the outer disk suggests that the stellar disk may, in fact, possess a measurable outer cutoff, a radius beyond which essentially no disk stars are found. If that finding is confirmed, the cutoff lies well beyond the Sun, in the faint outer reaches of the bright galaxy. But even such a cutoff is not a constructed boundary. It is simply the distance at which the disk's gradual decline in stellar density reaches effectively zero. It is the end of a continuous decline, not the location of a wall. A cutoff, defined as the point where a fading reaches zero, is still a fading, not an edge in the ordinary sense. The journey has now crossed the first of the galaxy's edges. The bright disk, the component of the galaxy that defines its familiar appearance, lies behind. But the Milky Way does not end here. Beyond the bright disk lies a component that rarely appears in photographs because it emits very little light, the stellar halo, a large, roughly spherical distribution of the galaxy's oldest stars, extending far beyond the disk. The next part of the survey enters it, and with it, the geometry of the journey changes entirely. Part 4. The stellar halo. Beyond the bright disk, the structure of the galaxy changes fundamentally. For the entire journey so far, the survey has moved through a disk, a flat, thin component in which everything shares the same flattened geometry. The disk is now behind. The journey has entered the stellar halo, and the stellar halo is not flat. It is roughly spherical. This is one of the most important and least familiar facts about the Milky Way. Surrounding the bright disk, extending above it and below it, and well beyond its rim in every direction, there is a large, faint, roughly spherical distribution of stars. This is the stellar halo. The disk is the bright, flattened component that dominates photographs. The stellar halo is a dim, spherical component that rarely appears in them at all, and yet it extends far beyond the disk's outer rim. A complete picture of the galaxy requires both the bright, flat disk and the faint spherical halo enclosing it. The stellar halo contains only a small fraction of the galaxy's total stars. Its stellar density is very low, lower even than the thinned outer disk the journey has just crossed. But those sparse stars are distributed through an enormous volume, a spherical region several times larger across than the disk. In terms of physical extent, the stellar halo is a far larger structure than the bright disk, even though it contains far fewer stars. It is a large, faint, sparse structure rather than a small, bright, dense one. The stars of the halo differ from the stars of the disk in several measurable ways, and each difference is informative. First, they are old. Halo stars are among the oldest stars in the Milky Way. They formed early in the galaxy's history, before the disk had settled into its present thin, ordered configuration. The stellar halo is, in effect, a population left over from the galaxy's formation. Second, they are poor in heavy elements. Heavy elements, meaning all elements beyond hydrogen and helium, are produced inside stars and dispersed into space when stars die. They accumulate gradually in the interstellar medium over successive generations of stars. Halo stars formed before many generations had passed, when the gas had not yet been enriched, and so they contain only small quantities of heavy elements. Their chemical composition is a record of the conditions in the early galaxy. By measuring the composition of halo stars, the early history of the Milky Way can be reconstructed. Third, the halo stars move differently from disk stars. The stars of the disk all orbit in the same direction, in the same plane, in an ordered rotation, like a single coordinated system. The stars of the halo do not. They travel on long, steeply inclined, randomly oriented orbits, plunging inward toward the galactic center and then climbing back outward again, each star following its own independent path. The halo is not a rotating structure. It is a swarm of stars on individual orbits, distributed through a roughly spherical volume. It has no single direction of rotation and no defined plane. Within this faint spherical distribution are its most prominent features, the globular clusters. A globular cluster is a dense spherical grouping of stars, typically containing hundreds of thousands of stars, bound together by their mutual gravity into a stable sphere. The Milky Way's halo contains roughly 150 globular clusters. Each one is a compact, self-contained system of stars, dense enough to hold its spherical shape against the disruptive forces of the galaxy. The globular clusters are extremely old, among the oldest structures in the galaxy. They formed early and have maintained their compact spherical form for billions of years. They orbit the galactic center on long, slow paths through the halo. The most distant known globular clusters orbit well over 100,000 light-years from the galactic center, far beyond the bright disk. They are the principal landmarks of the halo, dense, identifiable concentrations of stars distributed through an otherwise sparse and featureless spherical volume. The internal density of a globular cluster is high enough that, from a position within one, the night sky would contain thousands of stars bright enough to be prominent, a sky far richer in visible stars than the sky seen from Earth. The stellar halo also contains a second category of structure, the stellar streams. A stellar stream is a long, thin filament of stars, extending across a large arc of the sky, in some cases wrapping a substantial fraction of the way around the galaxy. Each stream has a documented origin, and the origin is consistent across all of them. Each stream was once a separate object, a small dwarf galaxy or a globular cluster that approached the Milky Way too closely. The galaxy's gravity acted on that object over hundreds of millions to billions of years, stretching it. Its stars were drawn out, both ahead of and behind the original object, into a long filament. The original object dissolved, and the filament remained, orbiting through the halo as a thin stream of stars. The halo contains many such streams. They overlap and cross one another, and collectively they constitute a record of the smaller objects the Milky Way has absorbed over its history. The largest known stream is an extended arc of stars drawn from a dwarf galaxy that is still being pulled apart, still in orbit, still in the process of dissolving into the halo. The process can be observed in progress. This process explains a point raised earlier in the journey, that some stars in the outer disk did not originate in the Milky Way. The streams are the visible mechanism. The Milky Way grows, in part, by absorbing smaller galaxies. When a small galaxy is drawn in and pulled apart, its stars are not destroyed. They continue to exist, and they continue to orbit, now as part of the larger galaxy. The stellar streams are the record of that process, written in the distribution of stars across the halo. This is a general pattern in how galaxies form. Large galaxies assemble over billions of years, partly by accumulating smaller ones. The Milky Way's stellar halo, with its streams and its many globular clusters, is direct observational evidence of that assembly history. The halo is, in effect, an archive of the galaxy's growth, and the streams within it are individual entries in that archive, each one recording the absorption of a specific smaller object. The reading of that archive has become increasingly detailed. By precisely measuring the positions, motions, and compositions of very large numbers of halo stars, astronomers can identify groups of stars that share a common origin, stars that, despite being scattered across the sky today, move in coordinated ways and have matching chemical compositions, indicating that they were once part of the same smaller galaxy. Several such groups have been identified, each corresponding to a distinct galaxy that the Milky Way absorbed at some point in its history. The stellar halo, examined closely enough, resolves into the combined debris of a series of identifiable past mergers. The early Milky Way was not a single object that simply grew. It was assembled from a number of smaller galaxies, and the halo records the assembly. The globular clusters fit into this picture as well. Some of the Milky Way's globular clusters appear to have formed within the galaxy itself. Others appear to have been brought in from outside, originally belonging to the smaller galaxies that were later absorbed. The globular cluster system, like the streams, is partly native and partly accumulated. The whole of the stellar halo, its scattered old stars, its streams, and its globular clusters, is a composite structure assembled over the galaxy's history from material that formed in many separate places. The halo is the most direct evidence available for how the Milky Way was built. The orbital character of the halo is worth one further note. Because halo stars move on long, plunging orbits that carry them inward toward the center and back out, some of them pass through the disk on their paths. A small number of the stars visible in the ordinary night sky are halo stars, ancient stars passing temporarily through the disk on their long orbits. The halo is not entirely a remote structure. Parts of it intersect the disk continually, and some of the galaxy's oldest stars are, at any given time, within the disk where the Sun resides. These stars can be identified by their composition and their motion. They are poor in heavy elements, and they move at high speed relative to the disk, on paths steeply inclined to its plane. They are visitors from the halo, passing through. The geometry of the halo is worth restating, because it represents a complete change from the structure of the disk. The disk is flat, thin, and rotating in an ordered way. The halo is spherical, vastly more extended, and composed of stars on individual, randomly oriented orbits with no shared rotation. To travel from the disk into the halo is to move from a flat, ordered system into a spherical, disordered one. The two components are so different in geometry, in stellar age, in chemical composition, and in orbital behavior that they are best understood as two distinct populations, formed at different times by different processes, occupying the same region of space. The disk is the galaxy's later, settled structure. The halo is the remnant of its early formation. The study of the stellar halo has practical importance beyond mapping the galaxy's extent. Because the halo stars are old and chemically primitive, and because the stellar streams preserve the identities of the smaller galaxies the Milky Way has absorbed, the halo functions as a historical record. By measuring the compositions, ages, and orbits of halo stars, and by tracing the individual streams, astronomers reconstruct the sequence of mergers and accretions by which the Milky Way assembled itself. The halo is not only a component of the galaxy's present structure, it is the primary evidence for how the galaxy came to exist. Each stream is a documented merger. Each population of halo stars with a distinct composition and orbit is the trace of a distinct event in the galaxy's history. It is also worth noting the sheer emptiness of the halo, because it stands in contrast to everything the journey crossed before. In the disk, even at its faint outer edge, stars are common enough to fill the sky. In the halo, the stars are so sparse and so widely separated that an observer positioned within it, away from the globular clusters, would see a mostly dark sky with only a scattering of faint, distant stars. The halo is the largest stellar structure of the galaxy by extent, and at the same time the emptiest. It is a vast, faint, slowly orbiting sphere of ancient stars, and it has surrounded the bright disk for the entire history of the galaxy, unseen in ordinary images, detected only by careful measurement. When astronomers map the outer stellar halo by carefully counting its sparse, scattered stars, they find that it extends to roughly 300,000 light-years from the galactic center before the star counts decline, effectively to zero. That figure is worth comparing directly to the disk. The bright disk is roughly 100,000 light-years across. The stellar halo extends to roughly 3 times that distance from the center. The familiar bright disk occupies only the small central region of a structure 3 times larger in extent. The detection of the outer stellar halo deserves a note, because it illustrates how difficult these measurements are. The outermost halo stars are extraordinarily sparse and faint. To establish that the halo extends to roughly 300,000 light-years, astronomers must identify individual stars at enormous distances and confirm that they belong to the halo rather than being foreground stars of the disk or background objects. This requires precise measurements of distance, motion, and composition for very faint objects. The outer boundary of the stellar halo is, for this reason, less precisely known than the inner structure of the galaxy, and the figure of 300,000 light-years carries real uncertainty. What is certain is that the stellar halo extends far beyond the bright disk. The exact distance at which its stars finally fade to nothing is a measurement still being refined. The stellar halo also raises a question of definition worth stating plainly. If the halo's stars simply fade with distance, with no sharp boundary, then any figure for the halo's edge is, like the figure for the disk's edge, a convention. It marks the distance at which the star counts have declined to a value close enough to zero to be called the edge. A different choice of threshold would yield a different figure. This is the same situation encountered at every boundary in this journey. The stellar halo, like the bright disk before it, does not end at a line. It fades, and the edge of the starlight is the name given to the region where that fading becomes effectively complete. That outer limit of the halo is the second of the galaxy's edges. It is the edge of the starlight, the distance beyond which the Milky Way, measured by its stars alone, is effectively no longer present. But, as with the edge of the bright disk, it is a gradual decline rather than a sharp boundary. The star counts fade smoothly toward zero. There is no wall, only a continuous decrease in density. And, as before, the edge of the starlight is not the edge of the galaxy. There is more of the Milky Way beyond the last of the halo stars, and the component that lies beyond is not made of stars at all. It is gas. The next part of the survey enters the galaxy's gaseous halo, a structure that extends farther than the starlight reaches. Part 5. The gaseous halo. The journey has now passed beyond the stars. The bright disk lies far behind, and the faint stars of the stellar halo have thinned to near nothing. Measured by starlight alone, this would appear to be the limit of the galaxy. But it is not. The Milky Way continues outward in a form that emits almost no visible light. The journey has entered the galaxy's gaseous halo. The Milky Way has an extended atmosphere of gas. Surrounding the disk and the stellar halo, and extending farther outward than the starlight reaches, is a large diffuse envelope of gas. The technical term for it is the circumgalactic medium. It can also be described, more simply, as the galaxy's gaseous halo. The journey is now within it. This gas is extremely diffuse. It is far less dense than any vacuum that has been produced in a laboratory on Earth. Within a large volume of it, only a scattering of individual atoms would be found. But the gaseous halo occupies an enormous volume, and the total mass it contains is substantial. Current measurements indicate that the gaseous halo may hold a large fraction of all the ordinary matter in the Milky Way, possibly an amount comparable to all the stars combined, possibly more. By mass, the galaxy's diffuse gas is a major component, not a minor one. This is a point worth emphasizing. A component of the galaxy that is invisible to ordinary observation may contain as much matter as everything visible. Much of this gas is hot. It has been heated to temperatures of hundreds of thousands of degrees, and in places to millions of degrees. At those temperatures, the gas does emit radiation, but it emits it in wavelengths the human eye cannot detect, primarily in the form of low-energy X-rays. To observation in visible light, the gaseous halo registers as empty space. It is detected by instruments sensitive to other parts of the electromagnetic spectrum, and by the indirect methods this part of the survey will describe. The gas is not static. It is a slowly circulating reservoir, moving and turning across the volume around the galaxy. The gaseous halo is not a separate, inert shell around the galaxy. It is connected to the disk by a continuous exchange of matter, and that exchange is a defined and well-studied process. It is worth describing precisely. Cool gas in the halo, under the influence of the galaxy's gravity, drifts inward over long periods and settles onto the disk. There it becomes raw material for star formation. This is gas flowing into the galaxy's active regions, replenishing the supply that star formation continually consumes. In the opposite direction, within the disk, massive stars end their lives in energetic events that heat the surrounding gas and drive it outward, away from the disk, and back into the halo. The result is a continuous circulation, cool gas flowing inward onto the disk, hot gas being driven back outward into the halo. This cycle is sometimes called the galactic fountain. It has operated for billions of years, and it is the mechanism that has kept the disk supplied with the gas required for ongoing star formation. Without this circulation, the disk would have exhausted its star-forming material long ago. Not all of the gas in the halo originated in the disk. Some of it is gas flowing inward from intergalactic space, gas that has never been part of the galaxy before, settling toward the Milky Way for the first time, and eventually joining the circulation. The galaxy is therefore not a closed system. It continues to accumulate gas from the surrounding universe, and that accumulated gas becomes, in time, part of the material from which new stars are formed. The gaseous halo is not uniform. It contains clouds and filaments of cooler gas embedded within the hotter, more diffuse medium. Some of these filaments have the same origin as the stellar streams documented in the previous part. Just as the Milky Way's gravity draws stars out of its satellite galaxies, it also draws gas out of them. One prominent example is a long trailing filament of hydrogen gas, stripped from two of the galaxy's brightest satellite galaxies and extended across a large arc of the sky, following those satellites along their orbital path. The satellites themselves are the subject of the next part of the survey. Their gas is already present here, distributed through the gaseous halo, a sign that the journey is approaching the satellite's orbits. It is worth documenting how this gas is detected, because the method explains how a component that emits almost no visible light can nonetheless be measured in detail. The gaseous halo is studied largely by observing light from bright, distant objects far beyond the galaxy, and measuring how that light is altered as it passes through the Milky Way's gas on its way to Earth. The gas absorbs specific, characteristic wavelengths from the background light, leaving a measurable signature, a set of dark lines in the spectrum of the background object. From those absorption signatures, the composition, temperature, density, and motion of the intervening gas can be reconstructed. The galaxy's gaseous halo is therefore mapped not by observing it directly, but by observing its effect on light that passes through it. This is a recurring theme in the study of the galaxy's outer regions. The most extended components are detected indirectly by their effect on light and on the motion of other objects. The location of the gas edge is the key point for the central question of this documentary. The gaseous halo extends farther from the galactic center than the stellar halo does. The galaxy's gas reaches into regions where the starlight has already declined to zero. The journey has crossed the edge of the bright disk and the edge of the stellar halo, and it is now established that the gas extends beyond both. This is a third boundary, larger than the previous two, enclosing them. The existence of the gaseous halo also resolves a long-standing problem in the study of galaxies, and the problem is worth describing. When astronomers add up all the ordinary matter visible in a galaxy like the Milky Way, the stars and the gas of the disk, the total falls short of the amount of ordinary matter that theory predicts the galaxy should contain. A significant fraction of the galaxy's ordinary matter appeared, for a long time, to be missing. The gaseous halo is a large part of the answer. A substantial quantity of the galaxy's ordinary matter is not in the stars or the disk at all. It is in the diffuse, hot, nearly invisible gas of the circumgalactic medium. The matter was not missing. It was simply in a form and a location that ordinary observation does not easily reveal. This is a recurring lesson of the outer galaxy. The components that are hardest to see are not minor, and in several cases, they contain more matter than the components that are easy to see. The temperature structure of the gaseous halo is worth one further note. The gas is not all at one temperature. It ranges from cooler clouds at temperatures of thousands to tens of thousands of degrees, embedded within a hot, diffuse medium at temperatures of hundreds of thousands to millions of degrees. The cooler clouds are denser and tend to fall inward toward the disk. The hot medium is more diffuse and more extended. The interplay between the two, the cool gas condensing and falling in, the hot gas being driven out and diffusing through the halo, is the detailed mechanism of the galactic fountain. The gaseous halo is not a static envelope, but a structured circulating system, with its own internal layers and its own slow dynamics. A clear pattern has now emerged, and it is worth stating directly. Each boundary the journey has crossed lies farther out than the one before it. The bright disk fades first. The stellar halo extends farther. The gaseous halo extends farther still. The galaxy is not a single object with one boundary. It is a series of nested components, each more diffuse and more extended than the one within it. The question of where the galaxy ends does not have a single answer, because the galaxy has multiple edges, and each lies at a different distance from the center. The gaseous halo is also the medium through which the galaxy interacts with the wider universe, and that role is worth describing. The disk of the galaxy is, in a sense, sealed off from intergalactic space. The gaseous halo is the layer in between. Gas arriving from intergalactic space does not fall directly onto the disk. It first joins the gaseous halo, mixes with the gas already there, and only later, after circulating, settles onto the disk. Likewise, gas driven out of the disk by dying stars does not escape the galaxy immediately. It enters the gaseous halo and circulates there, and much of it eventually returns. The gaseous halo is the galaxy's interface with its surroundings, the region through which matter enters and the region through which it leaves. It is, functionally, the outer boundary layer of the galaxy is a working system, even though, like every other component, it has no sharp edge of its own. The composition of the gaseous halo is informative as well. It is mostly hydrogen and helium, the elements that have been present since the early universe, but it also contains heavier elements. Those heavier elements can only have been produced inside stars. Their presence in the gaseous halo is direct evidence that the gas there is not purely primordial. Some of it has been processed through stars in the disk, enriched with the elements those stars produced, and then driven outward into the halo. The gaseous halo therefore contains a mixture, primordial gas arriving from intergalactic space and processed gas expelled from the disk. By measuring the proportions and the distribution of heavy elements, the history of the galaxy's gas circulation can be reconstructed in the same way that the composition of halo stars reconstructs the history of the stellar populations. The gaseous halo has been the most difficult component of the galaxy to map, and it was, in consequence, one of the last to be characterized in detail. Because it emits almost no visible light, and because it is detected mainly through its faint absorption signatures on the light of distant background objects, building a complete picture of its extent, mass, temperature, and structure required observations that earlier instruments could not make. The understanding of the gaseous halo presented here is therefore comparatively recent. It is a reminder that the map of the galaxy is not finished, and that the outer, fainter components are precisely the ones still being measured. The gaseous halo, like every component the journey has crossed, has no sharp outer boundary. It thins gradually with distance. There is no wall at the edge of the gas. There is only a continuous decline in density, the same gradual fading that has characterized every component of the galaxy so far. It is worth noting that the gaseous halo, despite its vast extent and substantial mass, would be entirely imperceptible to an observer passing through it. It emits almost no visible light. Its density is so low that an observer would register no resistance, no haze, no sign of it whatsoever. To direct human perception, the gaseous halo is indistinguishable from empty space. And yet it is a major component of the galaxy, containing perhaps as much ordinary matter as all the stars. This is one of the clearest demonstrations of a principle that has run through the entire journey. The visible galaxy and the actual galaxy are not the same thing. A complete account of the Milky Way must include components that emit no light, that register on no ordinary observation, and that are nonetheless real, massive, and structurally essential. The gaseous halo also sets up the final stage of the journey. The gaseous halo is the outermost component of the galaxy, made of ordinary matter, the ordinary matter being the protons and neutrons and electrons that compose stars, planets, gas, and everything familiar. Beyond the gaseous halo and beyond the satellite galaxies, the galaxy continues, but it continues in a form that is not ordinary matter at all. The final and largest component of the Milky Way is made of dark matter, and the gaseous halo is the last ordinary matter structure the journey will cross before reaching it. The transition from the gaseous halo to the dark matter halo is, in a sense, a transition from the part of the galaxy made of familiar material to the part made of something whose nature is still unknown. Beyond the gaseous halo, the journey reaches the outermost structures associated with the galaxy. First, the satellite galaxies, the population of smaller galaxies orbiting the Milky Way, which the next part of the survey examines. And beyond them, the largest and strangest component of the galaxy, the dark matter halo. The journey continues outward. Part 6. The satellite galaxies. The journey has crossed the bright disk, the stellar halo, and the gaseous halo. At this distance from the galactic center, the survey reaches the outermost structures associated with the Milky Way, a population of smaller galaxies in orbit around it. These are the satellite galaxies, and they mark the transition between the Milky Way considered as a single galaxy and the Milky Way considered as the dominant member of a larger group. The Milky Way is orbited by dozens of smaller galaxies. They are gravitationally bound to it, orbiting it in the same way that moons orbit a planet, though on far larger scales and over far longer periods. They are the largest discrete objects associated with the outer galaxy, and they occupy the regions the journey is now crossing. Most of the Milky Way's satellites are dwarf galaxies. They are small and faint, and many contain only a few thousand to a few million stars. For comparison, the Milky Way itself contains hundreds of billions of stars. A dwarf galaxy is a complete galaxy at small scale. It has its own stars, its own structure, and its own history. But it is many times smaller than the Milky Way's disk, and many of them would fit, several times over, within the volume of the disk alone. Many of these satellites are extremely faint, faint enough that they were not detected by direct observation in the ordinary sense. They were identified by statistical analysis, by detecting a slight excess of stars in a particular region of sky, an excess measured against the background star field, too subtle to register as a visible glow. Some of the Milky Way's satellite galaxies are barely distinguishable from the surrounding star field and were identified only through careful counting and statistical methods. The faintest satellites of the Milky Way are among the most difficult galaxies to detect anywhere, despite being among the closest. The dwarf satellites tend to contain old stellar populations. Their stars formed long ago, and most of these galaxies have little or no ongoing star formation. They are old, small, faint systems, orbiting in the outer regions of the Milky Way, composed largely of ancient stars. The reason most of them no longer form stars is connected to their orbits. As a dwarf galaxy moves through the Milky Way's gaseous halo, the gas of the dwarf galaxy is stripped away by its passage through that medium. In much the same way, the bright satellite's gas is being drawn into the trailing filament documented in the previous part. Without gas, a galaxy cannot form new stars. Many of the dwarf satellites have had their gas removed by their orbits through the Milky Way's halo, and so their star formation has stopped, leaving them as old, quiet systems. The satellite galaxies vary considerably among themselves. The faintest contain only a few thousand stars and are barely larger in their stellar content than a large star cluster, though they are classified as galaxies because they are dark matter-dominated systems rather than simple clusters. The largest, the two bright satellites of the southern sky, contain billions of stars each and have their own internal structure, their own star formation, and their own smaller companions. Between these extremes lies a range of intermediate dwarf galaxies. The satellite system of the Milky Way is not a uniform population. It is a graded series, from objects barely large enough to be called galaxies up to substantial galaxies in their own right, all of them bound to the Milky Way and orbiting it. Not all of the satellites are faint. The two largest and brightest are visible to the unaided eye from the southern hemisphere. They are irregular galaxies, lacking the ordered spiral structure of the Milky Way, and they appear in the southern sky as two detached patches of light, clearly separate from the band of the Milky Way itself. They are substantial galaxies in their own right, each containing a significant population of stars, and they are close enough to the Milky Way to be prominent features of the southern sky. The satellite galaxies are directly connected to features documented earlier in this journey. The stellar streams in the halo and the filament of gas in the gaseous halo both originate with these satellites. The mechanism is the one described in the fourth part of the survey. Several of the satellite galaxies are currently being pulled apart by the Milky Way's gravity. Their stars are being drawn out into the streams that thread the stellar halo. The two bright satellites trail a long filament of stripped gas, the filament documented in the previous part. The journey passed the products of this process earlier, in the halo and in the gaseous halo. Here, at the satellite's orbits, it reaches the source. The satellites are observed to be on orbits that, in several cases, carry them gradually closer to the Milky Way over spans of billions of years. The galaxy is, slowly, drawing its satellites inward. Over very long timescales, many of them will be pulled apart and absorbed, exactly as earlier satellites already have been. The stellar streams in the halo are the record of that process completed. The satellite galaxies currently in orbit are cases where the process is still underway. The growth of the Milky Way by absorption of smaller galaxies, documented in the stellar halo as a historical record, can here be observed as an ongoing process. There is a structural reason these small galaxies persist as long as they do, rather than being pulled apart quickly. The dwarf satellites are dominated by dark matter. Their visible stars constitute only a small, bright core within a much larger mass of dark matter. That dark matter provides the gravitational binding that allows the dwarf galaxies to resist the Milky Way's tidal forces and retain their structure across long periods. This is the first direct encounter in the journey with dark matter as the dominant component of a structure, and it introduces the subject of the final part of the survey. Even at the scale of these small satellite galaxies, the visible portion is only a fraction of the whole. The greater part, here as everywhere in the journey ahead, is dark matter. The faint dwarf satellites are, in fact, the most dark matter-dominated objects known. In the faintest of them, the dark matter outweighs the visible stars by a very large factor. These galaxies are, in effect, small concentrations of dark matter with a sparse scattering of stars embedded in them. They are valuable to the study of dark matter precisely for that reason, because they contain so little visible material to complicate the measurement. The motion of their few stars gives a relatively clean reading of the dark matter that governs them. The satellite galaxies are not only structures the journey passes on its way outward. They are among the principal natural laboratories for studying the dark matter that the final part of the journey will examine. The arrangement of the satellite galaxies around the Milky Way is itself a subject of ongoing study. The satellites are not distributed uniformly. There is evidence that many of them lie roughly within a single broad plane, rather than being scattered randomly across all directions, and the reason for that arrangement is not fully settled. It may reflect the directions from which the satellites were accreted, the filaments of the larger cosmic structure along which matter flowed into the Milky Way's region. The satellite system, in other words, may carry a record of the galaxy's larger environment, of the structure of the matter beyond the local group from which the Milky Way and its companions were assembled. The outer galaxy is, in this sense, not a self-contained system. It is connected to and shaped by the larger universe around it. The two bright satellites, the pair visible from the southern hemisphere, are worth one further note. They are substantial galaxies, far larger than the faint dwarf satellites, and their gravitational influence on the Milky Way is measurable. The warp of the outer disk, documented earlier in this journey, is attributed in part to their pull. The satellites are not passive companions. The larger ones exert a measurable influence on the structure of the Milky Way itself, distorting the outer disk and stirring the outer halo. The galaxy and its satellites form a single interacting system. The satellite galaxies mark a particular transition in the structure of the survey. They are gravitationally bound to the Milky Way, They are part of its system. But they are also distinct galaxies, with their own stars, their own structures, and their own histories. At the orbits of the satellites, the definition of the Milky Way becomes less precise. The galaxy is no longer a single, isolated object. It is a galaxy accompanied by a population of smaller galaxies bound to it, and the question of where the Milky Way ends and its satellite system begins is, itself, a question without a sharp answer. The number of satellite galaxies belonging to the Milky Way is, itself, not a settled figure, and the reason connects to a theme of this journey. The bright satellites have been known for a long time, but the faint dwarf satellites are extremely difficult to detect, and new ones continue to be identified as surveys of the sky grow more sensitive. The known count has risen steadily as detection methods have improved. This strongly suggests that more faint satellites remain undetected, below the current threshold of detectability. The Milky Way's satellite system is, in all likelihood, larger than the confirmed count, and its true extent is limited by what can be observed rather than by what is there. This is the same situation encountered with the bright disk, whose apparent edge depends on detection limits. Throughout the outer galaxy, what is measured is constrained by what is faint enough to escape detection. The satellite galaxies also provide a measure of the Milky Way's total mass, and the method is worth noting. A satellite galaxy in orbit moves at a speed determined by the mass of everything interior to its orbit. By measuring the orbital speeds of the most distant satellites, astronomers can weigh the Milky Way out to large distances, including the mass of the dark matter halo. The satellite galaxies are, in this respect, instruments. Their orbits are measurements of the galaxy's total mass, extending to distances far beyond where the visible galaxy ends. They are the outermost objects whose motion can be used to weigh the Milky Way, and they indicate a total mass far greater than the visible components alone could account for, a result that points directly to the dark matter halo. Beyond the satellites lies a larger structure, which this documentary will note but not enter. The Milky Way is a member of the local group, a small cluster of galaxies whose other dominant member is the Andromeda Galaxy, a large spiral comparable in size to the Milky Way. The local group contains the Milky Way, Andromeda, and a few dozen smaller galaxies, bound together by gravity. The local group and the route from the Milky Way to Andromeda are subjects in their own right. The scope of this documentary is the Milky Way itself, and the journey stops at the galaxy's edge rather than continuing on to its neighbors. The satellite galaxies are the threshold of that scope. It is worth noting how the satellite galaxies fit the pattern this journey has traced through every component. Like the bright disk, like the stellar halo, like the gaseous halo, the satellite system has no sharp outer boundary. The satellites are distributed at a range of distances from the Milky Way, the most distant of them orbiting far out toward the limit of the galaxy's gravitational influence, and there is no clear line separating a satellite that belongs to the Milky Way from a small galaxy that does not. The boundary of the satellite system, like every other boundary in this survey, is gradual. The most distant satellites orbit in the same regions the dark matter halo occupies, and whether a given distant dwarf galaxy should be counted as a satellite of the Milky Way is, in some cases, a question without a definite answer. The satellite system fades in its own way, exactly as every other component does. The survey has now documented the bright disk, the stellar halo, the gaseous halo, and the orbiting satellite galaxies. One component of the galaxy remains, and it is the largest of all. It cannot be seen by any instrument, and it constitutes the majority of the galaxy's total mass. The final part of the journey examines the dark matter halo, and with it, the true outer limit of the Milky Way. Part 7. The dark matter halo. The journey has reached the final and largest component of the Milky Way. Beyond the bright disk, beyond the stellar halo, beyond the gaseous halo, and beyond the orbits of the satellite galaxies, there is a region that contains no stars, no luminous gas, and no visible structure of any kind. By every method of direct observation, it appears empty. And yet, it is the largest part of the galaxy, and it constitutes the majority of the galaxy's mass. The journey has entered the dark matter halo. It is worth registering the distance the journey has now covered. The survey began at the Sun, 26,000 light-years from the galactic center, and it has crossed the bright disk, the stellar halo, the gaseous halo, and the orbits of the satellite galaxies. The dark matter halo extends to roughly 1 million light-years from the center. The journey has reached the outermost region of the Milky Way, a region whose distance from the galactic center is measured in the hundreds of thousands and approaching the millions of light-years. This is the farthest the survey will go, and it is, by a wide margin, the most remote of all the galaxy's components. This is the central structural fact about the Milky Way, and it requires a precise statement. Surrounding the entire visible galaxy, the disk and the stellar halo and the gaseous halo together, there is an enormous, roughly spherical distribution of matter that emits no light, absorbs no light, and does not interact with light at all. It is detected by one means only: its gravity. Its presence, its mass, and its distribution are all established by measuring the gravitational effect it has on the objects and the light around it. This dark matter is not a minor addition to the galaxy. The dark matter halo contains more mass than all the stars and all the gas combined. By the best available measurements, the large majority of the Milky Way's total mass is dark matter. The bright disk, with its hundreds of billions of stars, is a small luminous feature embedded within a far larger and entirely dark structure. Everything visible in the galaxy, every star, every nebula, every spiral arm, the entire luminous galaxy documented in the earlier parts of this journey, constitutes the minor fraction of its mass. The dark matter is the major fraction. The dark matter halo is the component that holds the galaxy together. This is its measurable function, and it is how the dark matter was first identified. The stars in the outer disk, and the stars, clusters, and streams of the halo all orbit the galactic center faster than the gravity of the visible matter alone could explain. The visible mass, the stars and the gas, is not sufficient to produce the orbital speeds that are observed. A large quantity of additional, unseen mass is required, and the gravity of the dark matter halo supplies it. Without the dark matter halo, the galaxy could not maintain its observed structure. The outer stars, orbiting too fast for the visible mass to retain them, would not be bound to it. The dark matter is what binds the Milky Way into a stable galaxy. The methods used to detect dark matter are worth documenting in full because they establish how a component that emits no light can nonetheless be measured precisely. There are two principal lines of evidence. The first is the motion of visible objects. The stars and gas in the outer galaxy orbit the center at speeds that the visible matter cannot account for. This was first established by measuring the rotation of galaxies. The outer regions rotate far faster than expected. The orbital speeds of the distant globular clusters, the satellite galaxies, and the stellar streams all indicate the presence of a large additional mass. By measuring how all of these objects move, the distribution of the dark matter that governs their motion can be mapped. Every star, cluster, and stream the journey has crossed has, through its motion, been registering the presence of the dark matter halo all along. The visible galaxy has been tracing the dark one continuously. The second line of evidence is the bending of light. When light from a distant object passes near a large concentration of mass, its path is deflected. This is a prediction of general relativity, and it is well confirmed. The dark matter halo, being massive, deflects the light of objects that lie behind it. By measuring that deflection, the mass and distribution of the dark matter can be determined independently, without reference to the motion of stars. The dark matter halo is therefore mapped twice over, by two independent methods. Once by the motion of the objects within it, and once by the bending of light that passes through it. The two methods agree, which is why the existence of the dark matter halo is regarded as well established. What that mapping shows is that the dark matter halo is not a perfectly uniform sphere. It is somewhat flattened, and it is not perfectly smooth. It retains structural irregularities that reflect the smaller dark matter halos it has absorbed over the galaxy's history. This is the same assembly process documented in the stellar halo, where the streams record the absorption of smaller galaxies. The dark matter halo carries the gravitational record of the same process, operating in the dark component. The galaxy has assembled itself, in both its visible matter and its dark matter, by accumulating smaller structures over billions of years. The dark matter halo and the stellar halo are records of the same history written in two different components. It is worth stating directly what dark matter is and what it is not. Dark matter is a form of matter that has mass and exerts gravity, but does not interact with light, and does not appear to interact strongly with ordinary matter by any force other than gravity. Beyond those properties, its precise nature is not yet known. The composition of dark matter is one of the major open questions in physics, and it is the subject of ongoing investigation. That the question is open does not make the dark matter halo any less real. Its existence, its mass, and its distribution are established by multiple independent lines of evidence that agree with one another. It is the composition, the question of what dark matter is made of, that remains to be determined. It is worth being precise about how strong the evidence is, because dark matter is sometimes misunderstood as a speculative idea. It is not. The evidence for the dark matter halo comes from several independent directions, and they converge. The rotation of the galaxy requires it. The orbital speeds of the satellite galaxies and globular clusters require it. The bending of light by the galaxy's mass requires it. Beyond the Milky Way, the motions of galaxies within clusters require it, and the patterns in the relic radiation left over from the early universe require it, in consistent amounts. Many independent measurements, of many different kinds, all indicate the presence of the same additional mass. What remains unknown is not whether the dark matter halo exists, but what the dark matter consists of at the level of individual particles. The structure is established. The composition is the open question. The role of dark matter in the formation of the galaxy is also worth documenting, because it explains why the dark matter halo is the largest component. In the early universe, the first structures to form were concentrations of dark matter. Because dark matter does not interact with light, it was able to begin gathering under gravity earlier and more freely than ordinary matter. These early dark matter concentrations formed a gravitational framework, and ordinary matter, the gas that would become stars, then fell into that framework and collected at its centers. The visible galaxy formed inside a dark matter halo that was already there. The dark matter halo is not an addition to the galaxy. It is the structure within which the galaxy formed, and it remains the largest and most extended part of what the galaxy is. This reframes the entire journey. The bright disk, the stellar halo, the gaseous halo, every visible component the survey has crossed, formed within and is held by the dark matter halo. The visible Milky Way is the luminous material that collected at the center of a far larger dark structure. When the question is asked, where does the galaxy end? The most complete answer concerns the dark matter halo, because the dark matter halo is the galaxy's true extent and the galaxy's true outer limit. The visible components are nested inside it. The dark matter halo also explains, in retrospect, several features the journey encountered earlier. The high orbital speeds of the outer disk stars are explained by it. The orbits of the globular clusters and the stellar streams are governed by it. The satellite galaxies are bound by it, and their own internal dark matter is part of the same phenomenon. The warp of the outer disk and the slow distortions of the halo occur within it. Throughout this journey, the survey has been crossing structures whose motions and shapes are determined by the dark matter halo, and only now, having reached it, can those earlier observations be fully accounted for. The dark matter halo is not only the outermost component, it is the component that governs the behavior of all the others. The extent of the dark matter halo is the final measurement of this journey. The dark matter halo extends far beyond every other component of the galaxy. It reaches plausibly to roughly 1 million light-years from the galactic center, and possibly farther. That figure should be compared directly to the others the journey has established. The bright disk is roughly 100,000 light-years across. The stellar halo extends to roughly 300,000 light-years from the center. The dark matter halo may extend to a radius 10 times the diameter of the bright disk. It is, by a wide margin, the largest component of the Milky Way, and it is the component that cannot be seen by any means. At that great distance, a notable condition is reached. The Milky Way's dark matter halo extends far enough that it begins to overlap with the dark matter halo of the Andromeda galaxy, the other large spiral of the local group. The two galaxies, measured by their visible components, are separated by a great distance, a gap of millions of light-years. But measured by their dark matter halos, their outermost and most extended components, the two galaxies are already in contact. The Milky Way and Andromeda meet in their dark matter long before they meet in any visible form. And the dark matter halo, like every component the journey has crossed, has no sharp outer boundary. Its density declines gradually, with distance. It thins outward until the gravitational influence of the Milky Way is no longer the dominant influence, until the galaxy's gravity becomes one influence among many in the surrounding universe. The true edge of the galaxy, the outermost edge of all, is the distance at which the Milky Way's gravitational influence ceases to be the controlling one. It is not a wall. It is the point at which the galaxy's gravitational dominance fades into the general gravitational field of the wider universe. The overlap of the Milky Way's dark matter halo with Andromeda's deserves one further note, because it has a consequence for the future. The two galaxies are not only in faint contact through their dark matter halos, they are also moving toward each other. Over a span of billions of years, the Milky Way and Andromeda are expected to draw together and eventually merge into a single, larger galaxy. That is a process for the distant future, far beyond any human timescale, and it lies outside the scope of this documentary. But it is worth noting that the edge of the galaxy, the outer dark matter halo, is not a static boundary. It is the region where the Milky Way's structure first meets the structure of its largest neighbor. The edge of the galaxy is also, in this sense, the beginning of the galaxy's relationship with the wider universe. It is worth restating, as the survey of the dark matter halo concludes, how completely it reframes the question this documentary set out to answer. The journey began by asking where the Milky Way ends, with the bright disk in mind, the galaxy of the photographs. The survey has established that the bright disk is a small luminous feature within the stellar halo, that the stellar halo is itself enclosed by the gaseous halo, and that all of it is enclosed by and formed within the dark matter halo, which is larger than the bright disk by a factor of about 10, and which contains the majority of the galaxy's mass. The true Milky Way is the dark matter halo and everything nested inside it. The bright disk is not the galaxy. It is the visible center of the galaxy. The galaxy itself is far larger, mostly dark, and its outer limit is the outer limit of the dark matter halo. This is the final component of the Milky Way, and the journey has now reached its outermost extent. The survey has crossed every edge: the bright disk, the stellar halo, the gaseous halo, and the dark matter halo. The next and final part assembles the complete picture and states the answer to the question the journey set out to address. Part 8. The complete picture. The journey has reached the outermost extent of the Milky Way. The survey has moved outward from the Sun, through every component of the galaxy in turn, to the limit of the dark matter halo. This final part assembles the complete picture and states the answer to the question the documentary set out to address. Begin with the full structure of the galaxy, as the journey has documented it, from the inside outward. At the center, the galactic core and the central bar. Surrounding that, the bright disk, with its spiral arms, roughly 100,000 light-years across. The Sun is located within the disk, a little past the halfway point from the center, in the minor spiral feature called the Orion spur. Surrounding the disk, the stellar halo, a roughly spherical distribution of old stars, globular clusters, and stellar streams, extending to roughly 300,000 light-years from the center. Surrounding that, the gaseous halo, a diffuse envelope of mostly hot gas, extending farther still, and containing a quantity of matter that may rival all the stars combined. Distributed through the outer regions, the satellite galaxies, dozens of smaller galaxies in orbit. And surrounding everything, the dark matter halo, the largest component, extending plausibly to 1 million light-years from the center and constituting the majority of the galaxy's total mass. That is the complete Milky Way. It is a far larger and far more layered structure than the bright disk of the familiar photographs. The disk that defines the galaxy's appearance in every image and every illustration is only the small, luminous, central portion of the whole. Each component encloses the one within it, and each extends farther than the last, so that the galaxy, fully described, is a set of nested structures spanning a span of roughly 1 million light-years from the center to the outermost edge. Now, the central question: where does the Milky Way end? The journey set out to find the edge of the galaxy, and the answer, established by the survey region by region, is precise. The Milky Way does not have a single edge. It has several, and none of them is a sharp boundary. The survey crossed 4 of them. The edge of the bright disk, where the spiral structure fades, at roughly 50 to 60,000 light-years from the center. The edge of the stellar halo, where the last stars decline to zero at roughly 300,000 light-years. The edge of the gaseous halo, where the galaxy's diffuse gas thins away. And the edge of the dark matter halo, the outermost edge of all, where the galaxy's gravitational dominance fades into that of the wider universe at roughly 1 million light-years from the center. Each of these edges lies at a different distance. Each is a real, measurable feature of the galaxy. And critically, none of them is a wall. Every one of them is a region of gradual decline, a smooth fading of density with distance. This is the direct consequence of the principle established at the very start of the journey. The galaxy is built from density, and density fades. A structure assembled by gravity has no sharp boundary, because gravity itself has no sharp boundary. It only weakens, smoothly and continuously, with distance. So the precise answer to the question is this: the Milky Way does not end at a particular place. It fades, in stage after stage, through a series of nested components, each more diffuse and more extended than the one within it. The question of where the galaxy ends has not one answer but several, depending on which component is being measured, and every one of those answers is a gradual decline rather than a fixed line. The galaxy does not stop. Its density decreases continuously until it becomes indistinguishable from the surrounding universe. It is worth addressing, at the close, why the question was worth asking at all, given that the answer is that the galaxy has no single edge. The value of the question is in what the search for the edge reveals. To look for the edge of the Milky Way, one is forced to survey the galaxy completely, component by component, from the bright disk outward. And that survey reveals a galaxy far larger and far stranger than the familiar image. A galaxy whose visible disk is a minor part, whose mass is mostly invisible, whose structure is layered and nested across a span of 1 million light-years. The question of the edge is the thread that, followed, unwinds the whole structure of the galaxy. The answer, that there is no single edge, is less important than everything the search for it brings into view. There are several specific findings worth restating, because together they form the substance of this documentary. The bright disk, the part of the galaxy visible in every photograph, is only a small fraction of the whole, in both extent and mass. The stellar halo extends 3 times farther from the center than the disk does. The galaxy possesses a gaseous halo that may contain as much ordinary matter as all its stars combined, yet emits almost no visible light. The galaxy is orbited by dozens of smaller satellite galaxies, and it grows over time by gradually absorbing them, a process recorded in the stellar streams of the halo and still observable in progress. And the largest component of the Milky Way, the majority of its mass, is dark matter, a substance that emits no light, that holds the galaxy together, and whose precise composition is still unknown. It is worth restating the scale of the journey, because the numbers have accumulated across the survey and the full range is now visible. The journey began at the Sun, 26,000 light-years from the galactic center. It crossed the edge of the bright disk at 50 to 60,000 light-years. It crossed the edge of the stellar halo at roughly 300,000 light-years. And it reached the outer limit of the dark matter halo at roughly 1 million light-years from the center. From the inner edge of the survey to the outer edge, the journey spanned a factor of nearly 40 in distance. The dark matter halo, the outermost component, is roughly 10 times the diameter of the bright disk that the word galaxy usually brings to mind. The Milky Way, fully accounted for, is a structure far larger than its familiar image. It is also worth restating why none of the 4 edges is a wall, because it is the central finding of the documentary, and it rests on a single principle. Every component of the galaxy is a distribution of matter held together by gravity. Gravity weakens smoothly with distance and never stops abruptly. A distribution of matter assembled by gravity is therefore always densest at its center and progressively less dense outward, fading continuously, with no point of abrupt termination. This is true of the bright disk, of the stellar halo, of the gaseous halo, and of the dark matter halo alike. All four fade. None of them ends. The galaxy has four edges, and all four are gradual declines, because the single force that built all four components is itself gradual. There is one further observation that emerges from the journey as a whole. The galaxy, examined from the inside outward, is a stable and ordered structure at every distance. The outer regions are not hazardous, and they are not precarious. A star at the edge of the disk orbits as stably as the Sunday. The dark matter halo has held the galaxy together for billions of years and will continue to do so for billions more. The Milky Way is not a structure under strain. It is a structure in stable, long-term equilibrium, bound together by the gravity of its dark matter halo. The Sun and the Earth are located well within that structure. They lie a little past the halfway point of the disk, deep inside the stellar halo, deep inside the gaseous halo, and deep inside the dark matter halo that encloses everything. Every component of the galaxy that the journey crossed on its way outward also encloses the Sun's position. The edge of the galaxy, in all four of its forms, lies far beyond the Earth, at distances measured in hundreds of thousands and millions of light-years. From the position of the Earth, every edge of the Milky Way is remote. One further reflection follows from the survey as a whole, and it concerns the relationship between what is visible and what is real. At every stage of this journey, the components that were easiest to see turned out to be the smaller part of the story. The bright disk is conspicuous, and it is a minor fraction of the galaxy's extent and mass. The stellar halo is faint, and it is 3 times larger than the disk. The gaseous halo is nearly invisible, and it may hold as much ordinary matter as all the stars. The dark matter halo is entirely invisible, and it is the largest component and the majority of the galaxy's mass. The pattern is consistent, and it is worth stating directly. In the Milky Way, visibility is not a measure of importance. The most extended and most massive components of the galaxy are the ones that emit little or no light. A galaxy understood only by what it shines is a galaxy mostly unaccounted for. That completes the survey. The journey began at the Sun and moved outward through the bright disk, the stellar halo, the gaseous halo, the satellite galaxies, and the dark matter halo to the outermost limit of the Milky Way. The question was where the galaxy ends, and the finding is that it does not end at a line. It fades, gradually, through a series of nested edges into the wider universe. The Milky Way is a single, vast, layered structure, far larger than its visible disk, held together by the gravity of an unseen halo, and fading gently at its limits, rather than stopping. The Earth, and everything on it, is held securely within it, far from any edge. It is worth noting what the journey did not include, because the omissions define the documentary's scope. The survey did not continue past the satellite galaxies into the local group. It did not cross the gap to the Andromeda galaxy. It did not address the larger structures, the clusters and the cosmic web, of which the local group is a small part. Those are real, and they are vast, and they lie beyond the edge this documentary set out to find. The journey's scope was the Milky Way itself, from the Sun to the outer limit of the dark matter halo, and within that scope, the survey is complete. The galaxy has been crossed, from a position a little past the center of its disk to the farthest reach of its outermost component. It is also worth restating the position of the Earth within the complete structure, because it is the most direct answer to the concern that the question of the galaxy's edge can raise. The Earth is not near any edge. It orbits the Sun, which lies a little past the halfway point of the bright disk. The bright disk is enclosed by the stellar halo. The stellar halo is enclosed by the gaseous halo. And all of it is enclosed by the dark matter halo, which extends 10 times farther still. The Earth is therefore deep within the galaxy, enclosed by every one of its components, with the nearest edge tens of thousands of light years away, and the outermost edge roughly 1,000,000 light years away. Whatever the edge of the galaxy is, it is remote from the Earth, and the Earth's position is a stable and deeply interior one. Let the structure of the galaxy settle in the mind as the documentary closes. The bright disk turning slowly. The faint spherical halo of ancient stars surrounding it. The diffuse gas beyond that. The dark matter halo enclosing all of it. A galaxy with no wall anywhere, only a long and gradual fading at its furthest reaches. Let your breathing slow. Let your shoulders ease. Let the day settle behind you. The galaxy holds its shape, as it has for billions of years, and the Earth rests securely within it, far from any edge. Sleep well, and good night.